Now that we have our serial ports set up to talk to the chip, let's review what is in Array43, the application which you're going to run on the PC immediately. There's a lot there. There is a manual, DB013. We do believe in writing documentation, and I believe in reading it before using something so I know what I'm doing, rather than breaking a bunch of stuff and having to worry about how to fix it first. So let's take a close look at what's in here, looking at the table of contents. After we get past the introductory material, there is a section here on the structure of Array43. You should get familiar with this because there are two components to it. There is software running on the PC, which is used until you don't need it any longer, to assemble code and put it into the chip and to run it, or to inspect and change things going on in the chip. There is also Polyforth running on the chip itself. Both of these can develop code for the chip. Both of these can make applications and run them. We constitutionally prefer to work on the target hardware whenever feasible, but because the target hardware doesn't come with a boot medium or anything like that built in, we sort of have to work our way into it. As most of our boards are shipped, they are shipped with something on them that will run Polyforth already, but you're not guaranteed of that, particularly with boards made by other people. So using the PC is often essential before you can run Polyforth. So get familiar with this. Not every feature is present in each environment. For example, SoftSim is only supported in SaneForth on the PC, whereas injecting code in real time from inside of Polyforth into the chip is supported only in Polyforth. Mass storage organization and management tools, in addition to the standard things provided with Polyforth, we've got a concordance, which is very handy, and we've got a mechanism for printing listings, which are produced as PDF files automatically. Programming the F18 describes the assembler and the whole structure of what's on the disk for managing code. We have source code and we also have object code. Now, it's unusual to have object code in a Forth system, but here we have to be able to produce a boot stream for the chip by going and grabbing some code that does this and some code that does that and putting it in various nodes. So it's actually very convenient to have object code in the disk structure and available to use. This section, Programming the F18, describes the organization of what we call bins and what you can do with them, and tools like Examine for looking at them and comparing them and seeing that they've been changed. Then there are the interactive testing mechanisms. That's one of the characteristics that distinguishes our IDE, which was the term we used for it in the 70s, from what became known as an IDE. We meant interactive development environment. Now you see integrated development environment, where integrated means there's a compiler and a text editor together. For us, it was we are into the chip. We are interactively testing code inside the chip. We are injecting code in. We're inspecting and changing memory and registers. We're looking at what's going on. We're able to test things in a microscopic way directly on the hardware, not in simulation. So interactive testing is a unique thing to our way of doing things, if you will. The external IDE is the one which is run serially from the PC using SaneForth. Presently, the internal IDE, which is designed but not implemented and published yet, is a mechanism whereby Polyforth inside the chip can reach out and fondle nodes inside the chip and see what's going on in them and inspect and change and execute. Preparing boot streams is, in fact, the whole mechanism for making a boot stream, which is something that you can inject over one of the boot nodes, such as a serial, asynchronous or synchronous serial. You can inject a boot stream using an SPI flash if you have one connected to the chip. Boot streams are injected by Polyforth into the chip through a thing called the snorkel to inseminate nodes that are not used by Polyforth on the chip with any desired code. And a boot stream is a standard format. And it basically is a mechanism whereby coming in through any of those vehicles, the boot stream contains code which by port execution can jam around on the chip and stick code into nodes and get it ready to run and start it running. We do a great deal with port execution, not just the boot streams, but also the interactive testing in the IDE is all done by port execution, which is why we are able to show you registers in the stack and memory without affecting those things. It doesn't require any actual code in the node to see what's going on in the node. It doesn't require any other mechanism either. It requires only port execution where we are able to reach into the node via a port and have the code presented at the port executed by the node to do as we wish, and what we wish in this case is show us what's going on in that node. Simulation testing with SoftSim can simulate up to 2 chips and does this in an instruction execution manner. It's not a genuine analog simulator such as we use when working with the design of the chip, but this will in fact simulate running an application that's highly parallelized on numerous nodes, and we'll show you what all those nodes are doing. It also is loaded usually by a boot stream, but it doesn't have to be. That's a tool that runs only on the PC. This practical example was written by Dean Sanderson a long time ago. It hasn't been updated, but it is a good example. Commissioning a new GA144A12 board is basically useful when you have got your boot flash screwed up. So we'll skip that for now. Reference material. This is all a code library for items that we have stored in a bunch of nodes worth of code out on mass storage, which you can bring into the application. For example, the SRAM cluster for managing static RAM through nodes 7, 8, and 9, and the snorkel and ganglion mechanism. Maintenance, see SANE 4th manual. This is all directed to the appropriate manuals. Now, installing and configuring for a Windows platform is very well documented here, and much of this material duplicates but amplifies considerably what we presented in previous videos. The code here for Mac and for Unix is not been updated recently. Now, when you see a heading in the table of contents in this manual that is highlighted yellow, it means either that it hasn't been implemented or that some part of what's inside that section has not been brought up to date. In this case, the problem is that we don't have any people within our organization who actively every day use Macs or Unix. And as a result, we're not able any longer to speak authoritatively about what the environment is like on those boxes. So caveat emptor a little bit here, and if you learn something about it that contradicts the manual, well, by all means, let us know. So we will now engage in a couple of activities that are simple to do at this point using aRAY4th to illustrate, but certainly not exhaustively show what we can do with it. Now that we have the serial line set up correctly, the COM ports for speaking to whatever board you're using, it's time to see if we can actually talk to it. The board, if it has an SPI flash, should have a no boot jumper to prevent the flash from being loaded into the nodes on the chip. If there is such a jumper, install the jumper to prevent the chip from booting from the flash. Then, having started aRAY4 using the appropriate one of the shortcuts that we supplied, in this case the one that's G144A12, here we are looking at the aRAY4 help screen. At this point, if we remember which serial port it was that we were using for the A port, say on the eval board, the port that goes to node 708 on the chip, then we will at this point say the number of that port, 4 space self-test. We are case sensitive here. These are uppercase unless spoken otherwise. All right. So we say that, bam, and off we're running. We are now running all these tests, and you can see the numbers up there updating. We update them for each test, which then applies to all the nodes that are being tested. So it doesn't change very rapidly because that's per test, not per node. The N runs is the number of actual test programs that have been put into a node and executed so far. And the test programs, of course, do various things. Quite often, the test program is running in the node next to the one under test, and the test is actually being done through a COM port using port execution, because that's the cleanest way to find out what's going on in a node. We're not depending on its ability to do anything but execute an instruction correctly. And we're done. When we get to having run all 11,520 test programs, we say OK, and that means, well, we are able to talk to the chip. The communications seem to be pretty reliable, and the chip appears to be running correctly. By the way, of course, we test every chip before it goes onto a board. If you get one that doesn't work, something is horribly wrong, and we need to know about it immediately. There is also a thing called auto test, which can be run on an eval board. If we say /space auto test, we are now testing the target chip through the host chip. We're communicating between the two using synchronous communication between nodes 300 on the two chips. This is not the fastest way in the world to do it, but it still beats the heck out of having to move the wire over to a different port to go through the appropriate node 708 on the target chip. And this will run just fine. Now, this test actually tests not only the target chip, but all the nodes in the host chip on the way to the target chip. And it also tests the ability of the two chips to communicate using the high-speed SerDes, which is only there guaranteed on the eval boards. It's not there necessarily on other boards. So we may stop at this node, or this test rather, 2113. This is the test that will fail if there is no high-speed SerDes connection between the boards. Otherwise, it worked. We are able to fully test all the nodes in the target chip using the host chip's connection to the target chip. If you're not using one of our eval boards, you may need to change the baud rate at which we are communicating with the chip due to longer cables or funkier connection between the two before you run, for example, auto tests or self-test. In this case, what you do is locate self-test. And having found it, you see that it is 1881 load. That means block 1881 is where the code is. 1881 list. There is the script, if you will, for running the self-test. Line 1 is where we set the port, which was on the stack, and the bit rate. If U-BPS, which is 921,600 here, nearly a megabit, is too fast, use the editor, which you've already studied according to the manuals, right? F for find 921,600. Replace it with, say, 38.4. Flush, and you're now ready to go. You say self-test, you'll be running much slower. Of course, we don't want to do that, so we'll put it back the way it was. At any rate, that's how to deal with that situation.